Welcome to topic 4 trigonometry, and this is lesson 8, angles of elevation and depression. So I'm going to ask you the question, how do we describe what the angle is when looking to the top of a very tall building like this one, the Burj Khalifa, from ground level? As you can see, standing some way back in Dubai from this building and looking up. So that's sort of the question we're going to look at answering in this lesson. And likewise, we might be standing on a cliff and we're looking down and we want to at a boat in the water down below, and we want to describe the angle which we're looking down at. So they're the sort of questions we're going to be looking at, and they're described by the angles of elevation and depression. So first of all, angle of elevation. Let's have a look. We've drawn a picture here on the right, and I'm going to go through the terminology. Point B is marked at a higher elevation or height than point A, as we see here on the drawing. And there's a line connecting them. There's also a horizontal line which is drawn out from point A in the same direction essentially as where B is. And we see it as an angle that we can now mark from the horizontal line coming up from A up to the line that connects AB. And so what we actually define is this: the angle theta is called the angle of elevation of B from A. Now we have angle of depression, and you might be starting to think, yes, this is going the other way. Well, let's have a look at how it's defined. Again, we've got this drawing, and I'm going to say that point B is a higher elevation or height than point A, just as it was in the previous drawing. So that's defined. However, we draw a horizontal line out from point B horizontally, but generally in the direction back towards where A is. And then what we see, because we're doing it from the perspective of standing at point B, the angle alpha, as it's marked here, is marked from the horizontal line coming out from B down to the line connecting AB, or the line AB. So finally, our definition is that the angle alpha is called the angle of depression of point A from point B. So very clearly, it's all about where you are looking or standing from, okay? And just interestingly, if we put these two concepts together on the one drawing, two horizontal lines, one coming out from B, one coming out from A, and we put those angles that we saw before, theta and alpha, you might see and recall from parallel lines theory that they represent equal angles. We know them to be alternate. They sit on either side of what we'd call a transversal for parallel lines, and so alpha and theta are equal. This is the first of our two worked examples, and we start off with a description and a drawing which has been assembled from that description. It says from a point P, and you can see it just marked there at the left hand side of that drawing, the angle of elevation of the top of a tree is 50 degrees, meaning that if you draw a straight horizontal line from P, effectively from the ground along the ground to the tree, and then you also have the line from P directly to the top of the tree, the angle marked out would be 50 degrees. Now, we're told that P is 8 meters, so 8 meters from that point P to along the ground to the base of the tree, and we're asked to find the height of the tree corrected 2 decimal places. Now you can see there the letter O and A, they've been marked in because it's already been considered as a right angle triangle, and relative to that angle 50 degrees, we know that the length 8 is our adjacent because it's the adjacent side, and our length that we want by the letter H is our opposite because it sits opposite to the angle 50 degrees. So first of all, we're going to identify the appropriate trigonometric ratio. We have opposite and adjacent, and that takes us to tan theta equals opposite over the adjacent as the rule that we should use. And just substituting in the values, which has been done on the next line there, we've substituted in for O the opposite, the letter H. We've substituted in for the adjacent, the number 8 that we're given. And we can put in, instead of theta, we can put in 50 degrees because we know theta. So then we're in a position whereby we can perform some rearranging of the equation. And to do that, we need to move the 8 across to the left-hand side, if you like. And then really what's then occurred is that whole left and right have been flipped around effectively, so that we end up with H equals 8 times tan 50 degrees. So putting that into the calculator and using our tan function, we find that H is equal to approximately 9.53 meters. Let's look at our second example, worked example. Given the description, the angle of depression from the top of a castle to a boat is 25 degrees. Let's bring up the picture, and it's got a few markings on it which we'll go through. And if the boat is 350 meters away from the base of the castle, how tall is the castle? So you can see there in the schematic that we have a castle, and effectively the top of a triangle's being drawn, but the top of the castle marks the top of this triangle. Coming down to sea level, if you like, we have a right angle, and then going out 350 meters out, we have the boat there 350 meters out to sea from the castle in the horizontal direction. Also, we're told that that angle of depression from the top of the castle is 25 degrees. So the 25 degrees that you see marked up the top there, just out from the top of the castle, there is a horizontal line shown as a dotted line in this case, and that's where the 25 degrees can be positioned. But interestingly, and it helps us, we can recognize that that 25 degrees is also the same as the 25 degrees that is made out between the sea level line, if you like, the horizontal line down the bottom, and the line between the top of the castle and the boat. They are alternate angles, so that's 25 degrees down there as well. And now we have what we need to start looking at a solution. We can recognize with an angle 25 degrees, we have a side which is adjacent, so we put the letter A there because we know that A has a length of 350. And we want to know the height, which is actually that value over there, which is opposite to the angle that we have, and we put an O there for opposite. It's also, we're going to call it a length X. Okay, so let's just have a look. And it's sort of, if you like, they've started off with the rule tan theta equals opposite over adjacent, and it's already been substituted, opposite's been substituted for the length X there in the equation, and in the numerator, in the denominator, the adjacent has been substituted for 350 meters. And on the left hand side, the theta value for tan, in front of tan, has been replaced by 25. So again, a rearranging of the equation, we're taking 350 across to the right hand side by multiplying both sides by 350. We're left with X on the right by itself, which is good, and on the right rather, and on the left we have 350 times tan 25 degrees. Putting that into the calculator gives us the value that X is equal to 163.2 meters. Seeing we've been asked to tell the answer to the nearest meter, we just simply round that off to 160 meters as the height of the castle. And bearing in mind that is the height, in this case, from sea level up to the top of the castle.